So what I want to do today is give us some working examples where we're going to first look at the torus and then the Klein bottle. And what we're going to do for these is calculate the homology, the cohomology, and the cup product. So we're going to review everything we've been talking about so far, and hopefully we're just working through an example will help all this stuff be really concrete. So let's first do it with the torus. And we'll go through homology pretty quickly, and then we'll talk about the cohomology and the cup product. So sure, let's call these A, these B. You form a torus by gluing together opposite sides of a sheet. When you do that, you get like a cylinder, and then you glue the top to the bottom to close it up into a torus. And I need some name for this guy, so call this some C. So now we have some delta complex structure. And I'll call this whole region down here, this 2 simplex, I'll call this the lower one, and I'll call this the upper one. Okay, great. So what is the homology of this guy? Well, we have a chain structure like this. And if we want to calculate the homology, we would say, well, C0, this is some vertex V, and all of these corners are identified, so you just have a single vertex V. So this is generated by a single vertex V, free abelian group generated by V. C1, you can think of as being generated by A, B, and C. And your C2 is generated by your U and your L. And now let's think about how these boundary maps work. That's just the 0 map. But in this case, A, B, C all get sent to 0 because the boundary of A is V minus V. And the boundary of B is V minus V. And the boundary of C is V minus V. So this is really just the 0 map. Each of these guys, A, B, and C, get sent to 0. How about this other boundary map? Well, if I'm at the upper guy, the boundary of the upper is B plus A minus C. You go in the direction, so we think of these arrows as pointing to the larger vertices, and so you begin here and you follow B, A, minus C, which is abelian, you can write as A plus B minus C. And L is also going to be A plus B minus C. So L is also going to get sent to A plus B minus C. And so now when we think about the homology, my H0 of the torus is just the kernel, which is of this 0 map, so it's all of V over the image. Well, there's no image, so it's just the map generated by V, which is Z. There's a abelian map. This is an abelian map generated by V, so it's Z. H1 of the torus is going to be the kernel, so it's A, B, and C. Mod out by A plus B minus C. You can think this is the relation C equals A plus B. So just saying C is defined in terms of A and B. So this is just A and B. C is defined in terms of them, which is the abelian group generated by A and B. So that's Z2. And H2 of T is the kernel of this map, while U minus L is the kernel of that map, minus the image of this map, which is 0. So this is just the group generated by u minus L, which is Z. And you should think u minus L really makes sense because I claim u minus L is this entire region, u and L. You might worry, shouldn't it be u plus L? But the reason it's not u plus L is because if I pick some orientation up here, this orientation is consistent with the orientation of u, whereas down here that orientation would be going against the orientation of L. And so that's why you would pick up a minus for the L, because the same orientation on this whole space travels with u but against L. And if you did the opposite orientation, it would be L minus u, right? But the point is, you should think about the region as a whole, if you think about this whole thing being a region, not as u region plus L region, but because of the orientation, the u minus the L. Okay, so that comes out in the homology nicely. So that's the homology of the torus. Let's think now about the cohomology. So let me just label this the homology. How about the cohomology? Well, we could do it all from scratch, where we invert these chains. So I think of C upper 0 being homomorphisms from this group to Z, and this being homomorphisms from here to Z, and so forth. And I can calculate the cohomology this way, the maps would get reversed, I can calculate it all out. But we've already seen that we have a universal coefficient theorem, that a theorem that tells you what is the cohomology in terms of the homology. And so I'll just remind you what it said. The nth homology of whatever, in this case the torus, with z coefficients, there's also one for other coefficients, but it's easiest with z coefficients. Do you remember what this comes out to be? It is the homology of the torus mod out by any torsion you might have. And so, okay, now this looks confusing because you think this might be the torus. This is not the torus, this is torsion. This is the torsion of the HN, right? So sorry if that causes confusion. And then you add to it the torsion of the previous guy. So if this is like H upper 2, it's the homology H2 mod out by its torsion, then add to it the direct sum with a torsion of H1. But torsion is just stuff like Z2, like Z sub 2, Z mod 2Z. Here there is no torsion. And so since there's no torsion, we have no torsion in the torus. It's kind of like a tongue twister. No torsion in the torus. Tori had no torsion in her torus. You can make that a tongue twister. Anyway, torsion. So then what that tells you is that your H upper n is just going to be, with z coefficients, is just the same thing as H lower n. I'll do an example, maybe when we do the Klein bottle, where we do something other than z coefficients. But for now, let's just work this out with z coefficients. So I know that my H upper 0 of the torus with z coefficients is also just going to be a copy of z, or isomorphic. These should all really be isomorphisms. Isomorphic to a copy of z. My H upper 1 of your torus with z coefficients is isomorphic to z squared. And my H upper 2 of my torus with z coefficients is isomorphic to z. Okay, now let's take a second and think about the dual elements of the basis of these guys. So these guys have basis that are the dual elements to these guys. So this z, you can think of it as just being generated by some nu, where that nu of v is 1. So this nu is like what does it mean to be in H0? It means that you're in C upper 0, which means that this nu is a homomorphism from C0 to Z, right? And all that C0 is the single element V. It's generated, it's all multiples of the element V. This is generated by the vertex V. And so these homomorphisms are generated by the map nu, where nu just, is it nu? You know Greek. Yeah. This is nu, right? After mu comes nu. This is the Greek letter nu? Yeah. Okay, this is nu. It looks like a V, that's why I picked it. Where this just takes V to 1, and that means like it would take 2 copies of V to 2, or 7 copies of V to 7, right? This is just copies of V, chains of V. Okay, that's not a very important one. The one I'm going to care about today is H1 and H2. Your H1 is just generated by some duals to your A and your B, so some alpha and beta, where these also just be homomorphisms from now C1 to Z, so they're going to be maps acting on A, B, and C. And the way these are going to act is just alpha of A is 1, alpha of B is 0. Beta of A is 0, beta of B is 1. So these are just the duals to A and B. However, since these are maps on C1, I also need to define how they act on C, right? So I need to know how these act on C. But for that, I need to respect this boundary condition. So I'm going to need to respect that the way it acts on C is just the way it acts on A plus B. So from the boundary condition, you just get that alpha of C should be the same thing as alpha of A plus B, which, since it's a homomorphism, is alpha of A plus alpha of B. So that would just be 1. And likewise, beta of C, since the boundary condition gives us that C is A plus B, this should just be beta, since you're modding out by boundaries, should just be beta of A plus B, which is beta of A plus beta of B, which is itself 1. And then finally, this guy is just generated by, well, something that corresponds to U minus L, my region. So I'll call it maybe the Greek letter rho, which is just the guy that will act on my region. So that rho of the whole region, that is rho of U minus L, is 1. Okay. Is that good? So the point is, these are just the duals of these guys, extended appropriately to respective boundary condition. So what we want to do now is talk about the cup product. So recall the cup product is a map from the jth cohomology group of some space with some coefficients. Here I'll just do z coefficients, but they can be whatever coefficients you like. And so it's a Cartesian, so it's from hj with hk of your space with the same coefficients, here I'll just z coefficients, to cup product takes you to something in hj plus k of x with z coefficients. And the case we're going to be really interested in is the map from h1 cross h1 to h2. So what we want to understand is how do you combine like an alpha and a beta somehow to map into this space? So what's the relationship? What's the map? So here's the particular one I want to solve. So this is the general formulation of the cup product. But I'm interested in the map from H1 to H1 into H2 of the torus with z coefficients. So here, there's going to be like several possibilities. I should think about like, what is A cup A? What is alpha cup alpha? What is alpha cup beta? What is beta cup alpha? And what is beta cup beta? That's what I want to understand. That's my goal. So this guy's generated by alpha and beta, so I want to understand how these cup together. And these all are going to be things that live in H2, which we said is just generated by some rho. So like, is this equal to rho? Is it equal to 2 rho? Is it equal to 0? Those are the questions we want to know. So that's the problem. That's what cup product is doing, is cup product is giving you a way of relating your elements of H1 with something in H2. Or in general, relating an element of Hj and an element of Hk with an element of Hj plus k. If this had some kind of H3, H3 is 0. So like, since H3 is 0, you know like alpha cup rho is just 0. And that follows from the fact that this is an H1, this is an H2, so the cup product is an H3, so that's just not very interesting. And likewise, beta cup rho is just 0, or like rho cup rho is just 0, because that would be something in H4, and there's no H4. So like, these are all trivial. But I want to know, is one of these non-trivial? Is there a way of cupping two of these guys to get out rho or some multiple of rho? Okay, so to do this, let's think back to how we had defined the cup product. So the cup product, this is something that lives in H2. And so what we should do is we should have something like alpha cup alpha. We should think, what does it do to, well, either of these regions? Ultimately, I want to think about what it's doing to R. So alpha cup alpha, this is in H2. And so since it's in H2, you can recall H2 is defined to be the kernel of the map from, make sure I get the direction right, from C2 to this boundary map, from C2 to C3 over the image of the boundary map from C1 to C2, right? This is right, this is what it means to be H2. I always screw up my indices. I think this is right. And so if you're in H2, you can think you're in the kernel of this, so you're something in C upper 2. So you can think of this as being represented by something in C upper 2. But C upper 2 is a homomorphism from C lower 2 to Z. So C upper 2 are homomorphisms from C lower 2 to Z. So you can think that what each of these guys is doing is it's a map that acts on something in C lower 2. And we said C sub 2 is just, well, U and L, which if you subtract them, it gives you R. So we can think about what it's doing in U and L, but ultimately we want to know what it's doing in R. So we should think like, what is this doing, say, on U? And then we can ask, what is it doing on L? So I don't want to have to keep running back every time. So let me copy again the picture of our torus so we can have it right here, it'll be convenient to work with. we had A on the bottom and top, B on the right and left, and C right here. And this was my upper region, and this is my lower region. So let's think about what alpha cup alpha is doing on U. U is a simplex, a 2 simplex. It has 3 vertices. This is the smallest vertex, because the arrows point to the bigger ones, then this one, then this one. Right? So if you want to label these, this would be like vertex 0, 1, and 2. So alpha cup alpha on U is defined to be alpha of U limited to this one simplex, B, times the second guy, alpha, on the next one simplex, A. Good? So if this is confusing, just remember, like, what's going on here is when you have something like this, V0, V1, V2, arrows pointing in the direction of the larger one, and you have some X cup Y acting on this whole 2 simplex. So I'll just call it V0, V1, V2. We had defined that to be whatever X does to the one simplex V0, V1 times whatever Y does to the one simplex V1, V2. So that is what I'm using here. Good? And what does this come out to be? Well, this is 0. This is 1. 0 times 1 is 0. Likewise here, you tell me, this is going to be alpha of, what's the first one simplex of the lower guy? A, alpha of A, that's just 1 times alpha of B, that's 0, so 1 times 0 gives me 0. So I can see then that alpha cup alpha of, say, the full region is just alpha cup alpha of upper minus lower, which, since it's a homomorphism, is alpha cup alpha of the upper guy minus alpha cup alpha of the lower guy, but that's just 0. So alpha cup alpha is just 0. No matter what you put into it, it's just 0. So this alpha cup alpha is just 0. Not very interesting. Okay, how about alpha cup beta? What is alpha cup beta of the upper? Well, that's going to be alpha of, we've already said for the upper it's first B, then A, right? So it's alpha of B times beta of A, and that's just 0 times 0, so that's 0. How about alpha cup beta of the lower? Well, now if the lower, the first one simplex is A, and the next one is B, so this is alpha of A times beta of B, which comes out to be 1. Okay, I'm a little bit unhappy, but that's okay. So because I picked my orientation in a dumb way, what I get now is alpha cup beta of the full region is alpha cup beta of U minus L, which comes out to be 0 minus 1, so negative 1. I do not like that being negative 1. That makes me deeply unhappy. So what I'm going to do is, instead of calling this kernel U minus L, we could have called it L minus U. And that would just be thinking about the orientation of going, instead of clockwise, counterclockwise, which is typically how we think about orientations anyway. Like, I should have caught this earlier. Typically, you would do your orientations counterclockwise, which makes the U be the negative. And so my region is L minus U. And so if I instead think of R as being L minus U, I then get positive 1. And isn't that nicer? Isn't that so much nicer? So up here, this should also be L minus U. Okay, so up to a choice of orientation, it just impacts the sign if it's positive or negative, but you get that it's 1. But this 1 here is just saying that this is the element that sends R to 1. That's saying that this corresponds with rho. That's saying that the alpha cup beta is really just the same thing as rho. Because rho is the map that sends R to 1. Right? So what we found is that the cup of alpha and beta is rho. So the cup of these two guys in H1, of the two generators of H1, gives you your generator of H2. So what this is secretly doing is giving you a ring structure on all of the cohomology groups together. Then now there's a way to combine things in H1 to get things in H2. We didn't have that for homology. We have a richer structure now of how these things interact as a cup product to give you things down here. Alpha times itself with cup product, 0. But alpha cup beta gives you rho. Very nice. How about beta cup alpha? What's going to happen? Can you see it? When you do it all the way out, for U, it's just going to be B and A. So it's going to be alpha of B, beta of A, which is 0. But, oh, sorry, this is beta and alpha. Flipped it. Beta and alpha, which is 1. 1 times 1. Whereas beta cup alpha of the lower is for lower, it's first A, then B. So it's beta of A, alpha of B, which is 0. And since I've reversed the orientation, my beta cup alpha of the full region is going to come out to be beta cup alpha, we said now it's L minus U, so 1 minus 0, no, L minus U, so 0 minus 1, so negative 1. Which means that beta cup alpha is negative rho, or you can think of it as negative of alpha cup beta. Here the cup product is anti-commutative. It won't always be anti-commutative. Sometimes alpha cup beta is beta cup alpha, sometimes it's negative. So it's up to sign it commutes. And it depends on the setting you're in. In a second, we'll do an example with the Z2. Of course, with the Z2, negative is the same thing as plus, and so these will just be the same. But it's either commutative or anti-commutative. And how about beta cup beta? I mean, do you need me to work this out? Can you see what it's going to be? Yeah, if you have AB or BA, both cases it's 0. So it's just going to come out to be 0. So if you cup a generator with itself, a generator of H1 with itself, you get 0. But if you cup the two different generators together of H1, it gives you the generator of H2. Okay, so hopefully this helped you see what the cup product is and how it works. And it gives you relationships between your different homology groups. If we had picked an example of some H3, H4, we could have also cupped H1 with H2 and so far on. But in this example, those are all trivial. So what I want to do is just one more example for today. Trying to make this really concrete. So we're going to do the Klein bottle. So we're going to modify our picture a little bit from the Torus to the Klein bottle. And now we're going to do things in Z2 coefficients. So we won't do that until we get to cohomology. We'll begin with just working in Z for homology. But once we get to cohomology, we'll work with Z2 coefficients. So you can see what happens when you're in different coefficients. Okay, so let me draw the picture of the Klein bottle. It's almost the same as a torus. You just put a twist in it. So you're going to have like this side is the opposite of that side, whereas these will line up. So like if I call these A, there's a twist on the one direction. So it's like here you just have a cylinder. glue the B's together, you get a cylinder. But then when you come back in, you do this little twist. You do a flip, and that corresponds to going inside instead of completing it outside. And I need to give this some name. So let me call this C. Okay. The nice thing about this is if I have my U and my L, is that my orientations are consistent. So if I have some orientation here that it goes with U, the same orientation also is consistent with L, which means here my region is just U plus L. These are consistent with the region of the orientation of the two simplices, I'm saying. Whereas in the torus, one of them had to be flipped. Okay, so let's think through the homology of this guy. So C2 was generated by this U and this L. C1 is generated by ultimately A, B, and C. And C0 is generated by the vertex, and this vertex gets glued to here, and then it gets glued here, and then it gets glued here. So all of this is just one vertex. And then this is just the zero map. Okay. Again, the boundary of A is just V minus V. The boundary of B is V minus V. The boundary of C is V minus V. So this is just the boundary, the zero map. Which means that my H0 of the Klein bottle is just the kernel, the guy generated by V, over 0. So it's the guy just generated by V, which is a copy of the integers. Now let's think about the maps from U and L to A, B, C. U gets mapped to A, B, minus C. And L gets mapped to CA minus B. Oh, sorry, CA minus B. Good catch. Okay. So now we have to be a little bit careful. What is my H1? What is H1? The kernel of this map is A, B, and C. But then we need to mod out by these guys. So how does this work out? Well, this can be thought of just saying that your C is generated by A plus B. So you just get A plus B. So you just have A and B. Now, what does this relation become? Well, your C is A plus B. So this is A plus B plus A is B. The B's cancel, so it's saying 2A is 0. So that's the same as the relation A plus A is 0, or 2A is 0. A plus A. So what does that come out to be? That's right, it's Z plus a copy of Z mod 2Z. That's what your H1 is. And then your H2, like, what is the kernel of this map? It should be 0, so can we see this? What's the kernel of this map? Why is this just 0? Yeah, there is no kernel here, right? Like you try to find a kernel and you ask like, x copies of u plus y copies of L, you want to be 0. And, well, okay, the boundary, this is x copies of the boundary of u plus y copies of the boundary of L, you want to be 0. And so then you're like, well, that means x times, okay, you solve the system of equations and you see that there's no solution. So the kernel is 0 and the image here is 0, so of course that's just 0. Great. So we just have h0 and h1. Yes, because that's the homology. Okay, good. We're going to have more interesting cohomology. So now we want to calculate the cohomology. But what I'm going to do is I'm going to do the cohomology with Z2 coefficients. And since we're doing Z2, we don't have this nice little shortcut that was only for Z. There is a result we had that did give us a way to calculate it for Z2, but maybe here it's worth actually calculating it out. So let me actually go the long route of calculating out the cohomology. Okay. So I need to make my chain complex. So I'm going to dualize this chain complex. So I'm going to look at C0, C1, C2, and that would still be 0 over here. Where we call C2 is just homomorphisms from C lower 2 to Z2 coefficients. So we're doing Z2 coefficients. So maps into Z2. And C1 is just homomorphisms from C lower 1, which is ABC, into Z2. And C0 is homomorphisms from C0 into Z2. But it's not too hard to see. Like C0 is just copies of V. So homomorphisms, like from V to Z2, is just this new guy again, where you just have that new of V is 1. So C0 is just generated by this new, where new is dual to V. And C1, we can just have generated by alpha, beta, gamma, where these are going to be the duals to your A, B, and C. Because we want to think of all homomorphisms from A, B, and C, and combinations of A, B, and C to Z2. But that's going to be built up of just the duals, where alpha of A is 1, and alpha of the other guys, B and C, is 0. And beta of A is 0, but beta of B is 1, and beta of C is 0, and gamma of A and B are both 0, but gamma of C is 1. So alpha, beta, gamma is just the duals to A, B, and C. And any homomorphism is just a linear combination of these guys, right? Because it's like, just ask, what does the homomorphism send A to? Maybe it sends A to 3, B to 5, and C to 7. Well, that's just 3 copies of alpha, plus 5 copies of beta, plus 7 copies of gamma, right? So this really is the basis for C upper 1. And C upper 2 is just going to be the dual to U and L. And so I'm just going to use mu and lambda for the duals, where mu of the upper is 1 and mu of the lower is 0, whereas lambda of the upper is 0 and lambda of the lower is 1. Okay. So these are my basis elements for these abelian groups that make up my cochain complex. there's a glaring mistake here. What is it? Arrows, yes. When I dualize, my arrows get reversed. And so you go from having the typical boundary map to having instead this delta map. So now we want to take a second to try to understand what these deltas do. Okay, so this is a good review. Okay, so what does delta, where's delta going to send V? So maybe I'll do this in white chalk again for a little bit. So where does delta send V? I'm sorry, nu. Where does delta send nu? Well, delta sends nu over here, right? So delta of nu is in C1. And so since it's in C1, it's acting upon my C lower 1. So delta of nu is itself a homomorphism from C lower 1 to V2. And we want to understand what is this homomorphism. So what I'm going to ask is I'm going to say, well, what does this homomorphism do to something in C1? Let's think about what it does to like A, for example. And then we can also think about what it does to B and C. I also will want to know what does it do to B and what does it do to C. What does it do to C? Okay, so how is this defined? What is delta of nu? Well, recall delta is defined by being nu of the boundary of A. So you flip it with the boundary map. And the boundary of A is just 0, V minus V. So this is just nu of V minus V, or nu of 0, which is 0. And it's the exact same thing for B and C. So this first delta map is itself just the 0 map. So now we want to think about this boundary map. How does this boundary map, what is going to be like delta of alpha? Well, delta of alpha is going to live here in C upper 2. And so I can ask, what does it do? So it's some homomorphism from C lower 2 to Z2. So I can ask, what does it do to something in C lower 2? What does it do to U? What does it do to L? So I can ask, what does this do to U? Well, that's just going to be alpha of the boundary of U. And the boundary of U is A plus B minus C. Alpha of A plus B minus C. And what does this come out to be? Just, this is 1, these are zeros, so it just comes out to be 1. Great. So it sends that guy to 1. Okay, I'm also going to want to think about what it does on the lower guy. So what does alpha do to the lower? Well, that's just alpha of the boundary of the lower. And the boundary of the lower is C plus A minus B. Which is again just 1, right? Okay, but now that we see how it works with alpha, it's the same game to understand how beta acts on the upper and what delta of beta does to the lower. So on the upper, this just becomes beta of the boundary of U. So it's just beta of the boundary of U. So it's just beta of this guy, which is still going to be 1. This is just beta of the boundary of L, so it's beta of C plus A minus B, which is negative 1. And delta of gamma of U is gamma of delta of U, which gives you a negative 1. And delta of gamma of L is gamma of the boundary of L, which is gamma of C, which is 1. The other guys disappear. Okay. So now what we can do, so this is the map, this is my map delta 1. So maybe I should keep track of this as delta 1. So now, when I want to go and calculate the cohomology of this guy, the H upper 1 of my Klein bottle with Z2 coefficients, it should be the kernel of this map over the image of this map. The image of this map is just 0. That sends V to 0. What is the kernel of this map? So like, you're saying like alpha plus beta should be in there?
Yes. Alpha plus beta on U is going to be 1 plus 1 is 2, which is 0. And
Good. Yeah, since we're in Z2, alpha plus beta is 0. So you know, these negative ones you can think of as positive ones. We're in Z2, right? And alpha plus beta on L is also 0. So that works. You can have alpha plus beta. You could do alpha plus gamma, or you could do beta plus gamma. You could do beta plus gamma. And note, if you have alpha plus beta and beta plus gamma, if you add them together, alpha plus beta plus gamma, you get alpha plus 2 beta plus gamma, but since you're in Z2, that's just alpha plus gamma. So you just need 2 of the pairs of 2 to generate it. So the kernel is generated by alpha plus beta and beta plus gamma. So, and since the image is trivial, this is your H1. So here's my H1. Okay, this is H1, which is equivalent to, since we're working over Z2, it's Z2 direct sum Z2, 2 copies of Z2. That's H upper 1. I didn't do H upper 0, but we could do that really fast. That would just be the kernel of this, which is everything, over the image, which is 0. So it's just generated by nu. So this is the guy generated by nu, which is itself just a copy of Z2. I'm really interested in the H1, but then let's say something about the H2 as well. What does this H2 come out to be? Well, it's the kernel now of this map, which is everything, mu and lambda, mod out by the image of this map. And what is the image? The image of this map is just oh man, okay. So, notice all of these act the same way, and what they're all acting as is they're sending U to 1 and they're sending L to 1. So really, the boundary of, say, like your alpha is acting the exact same way as what in this guy? What would send U to 1 and L to 1? Mu plus. So all of these are acting exactly the same as mu plus lambda. And so the image is just the guy generated by mu plus lambda. So it's mu and lambda generated by, mod out by mu plus lambda. And so since you're working in Z2, this is the same as just saying mod out by the relation that mu is equal to lambda. So you're left with just a single generator. You can pick if it's mu or lambda, it doesn't matter. But you have a single generator. which is the same as, if you instead want to do lambda, that's fine. Just one generator, so one copy of Z2. So one copy of Z2. Good. So now we know what our H1 is, and we know what our H2 is. Here's our H2. And so now we want to think, how might these guys cup to give me either mu or mu and lambda acting the same way, so I'll just think of it as mu. How do these guys cup to give me mu, or do they cup to give me something trivial? So what I want to think about now is I want to think about the cup product. This picture is a little bit modified. So in this picture we now have, oh, I put B's this time. That's okay, that was weird. And I had on the left a down arrow. And so I think this picture looks right now, because I'll be referring to it. Great. So I want to think about, like, what is the cup product of, say, alpha plus beta, cup, let's do alpha plus beta. Okay. And I can first think about what it's doing on top. So what is that doing to U? So the boundary of my U is A, well, the first simplex is A, the next simplex is B. So this would come out to be alpha plus beta of A times alpha plus beta of B. Because it's A and B are your two simplices. Well, alpha of A is 1, beta of A is 0, so just 1 plus 0, so it's just 1. And likewise, this is just 0 plus 1, so just 1. So this is just 1 times 1. So this is 1. And then we can ask, well, what would it be on the lower guy? What is alpha plus beta and alpha plus beta on the lower guy? And on the lower, it's going to now be CA. So it's alpha plus beta of C times alpha plus beta of A. This is 0 times 1, so that's 0. Is that what I want? Yes. Good. So if you want to know what it is on the entire region, U plus L, alpha plus beta on the entire region R, which is U plus L, would come out to be just 1 plus 0, which is 1. Which means that this cup product is acting the same way as, well, maybe this was already enough to see it's acting the same way as your upper, so the same as your mu, right? So even here, you could have seen that your alpha plus beta cup alpha plus beta is just acting like your generator for your H upper 2, which we're here calling mu. What happens if we mix them together? So you could do alpha cup beta, alpha plus beta cup, what's the second guy called? Beta plus gamma? Beta plus gamma. And let's just do it on the upper one. So this is going to come out to be in A, the first guy applied to A, which is 1. The second guy applied to B, which is 1. So it's 1 times 1, which is 1. And so that is also acting the same as mu x, because mu sends the upper to 1. So we also see that alpha plus beta cup beta plus gamma also acts like mu. And then finally, well, you can flip it. How about beta plus gamma cup alpha plus beta acting on, so this is actually where we're going to get into a little bit of trouble, because this is going to be 0. This is going to be 0. But if you did it on the full region for both of these, when you do it on the lower you have CA, which gives you 1, 1. So that gives you 1 here. The lower here gives you nothing because the C makes this 0. So it's 1 plus 0, so it stays 1. So both of these come out to be 1. So this is the same as commuting it when you think about it as acting on the full region. Alpha plus beta is also like mu, because mu on the full region comes out to be 1. Mu on the full region is mu of the upper plus lower, which is mu of 1. Mu of the upper is 1, plus mu of the lower is 0, so that's just 1. So that acts the same as mu does. Okay, so what's the last guy? Beta plus gamma, right? So everything else has come out to be a generator, so you might hope that beta plus gamma would also be the same secretly as mu. But now it's not, because on the upper, the first guy is evaluated on A, the second guy is on B. Well, the first guy comes out to be 0, so that's 0. Whereas on the lower, this first guy is being evaluated on C. Well, that's 1. But the second guy is evaluated on A. That gives you 0 there as well. So now you see when you evaluate on U plus L, you get 0. So beta plus gamma cup beta plus gamma comes out to be 0. So we're getting this larger ring structure where you can think of the elements of your generators of H1 as being guys that you can combine to get an element of H2. And in this case, if you pick 2 of the first generator, you cup him with the first generator, or you cup the first and second generator together, you get the generator of H upper 2, but not for the second generator. It's kind of strange. So that's how you do cup product. So hopefully this was a concrete example. We can do more examples, but I'll just stop there for today to see. Now we've seen the torus and the Klein bottle, how to calculate the homology, the cohomology, and the cup product. So hopefully this was a nice hands-on practical lecture for you.